Hello and welcome to our vodcast for MATH130. For this vodcast, we chose to explore calculus, mainly showing the concept of the derivative. The history of the derivative goes back to the 1600s, to the times of Isaac Newton and Gottfried Wilhelm Leibniz, who to this day we aren't quite sure who is credited with the title of the founder of the concept. However, it is apparent to us that both these people made use of infinitely small values, which later was redesigned in terms of limits, taken to zero, showing the concept of the derivative. But what is the derivative? The concept of the derivative mainly deals with the rate of change of a function over a small enough period of time. So for functions whose rate of change is constant, such as shown here as a graph of fx equals 2x plus 3, so this is a straight line with a y-intercept of 3, and the x-intercept was found to be minus 1.5 here. Now, to find the rate of change or slope of this function, the derivative, we can take the rise over run, showing the change of the y over change of x, which is here shown to be 3 over 1.5, which gives a slope of 2. However, for graphs where the rate of change is not constant, such as a graph of fx equals to x squared, this graph looks like this. Now you notice how these two graphs are different. This is a straight line with a constant rate of change. This rate of change changes at nearly every single point. It goes down, it changes, then it stops it here with a slope of 0. And then it continues to go back up, increasing at a different rate. So to compute the rate of change for the entire function or a single point on the function becomes difficult, as the rate of change is different at each point. This is where the concept of a derivative was developed to solve this problem. It states that over a small enough interval of time, the rate of change is almost constant. And if that small interval of time is taken closer and closer to 0, then this is known as the limit. So if it's taken as close to 0, we can then successfully compute the derivative of that point. So to do this, we use lines known as secant or the tangent, which is basically a straight line drawn on this graph. So to do this, we take a small enough point on the graph which looks like a straight line. You can choose it anywhere. So choosing it here, just drawing a little circle, we can then draw a straight line on this curve. So this is the tangent, the slope of these points. So we choose another point on the graph where we want to use our values. So choosing this point here. Now we can then draw a rise over run as shown in the previous example. Then we can compute the change of values of the y and x values, similar to the previous example, to find the rate of change, the derivative of this graph. Okay, so now I'll be showing you a graphical and numerical interpretation of the definition of the derivative, the formula. So this will be shown on this graph of computing values of f x plus h here. This is fx, this will be x, and this will be x plus h. Now the formula is derived from minusing x plus h from x and minusing x plus h from x. This is shown by, let's draw here. So you have f, function of x, fx plus h, minus this fx over x plus h minus x. So then we can cancel off these, which gives us fx plus h minus fx over h. And from this, we take h as the limit h shrinks to 0.
Welcome to the continuation of our vodcast. I'll be explaining to you the second derivative, what it is, why is it useful, how can it relate to the first derivative. So we know the first derivative, what it is, it's a rate of change. It's a rate of change. Second derivative is pretty much the rate of change of the first derivative. So in other words, how fast is our rate of change changing? This is what this is. Our second derivative is pretty much how fast is our rate of change changing. You can think of it as sports cars when they say, oh, this particular sports car goes from 0 to 60 in 2 seconds, or 0 to 60 in 6 point something seconds. That's kind of what we're talking about here. So I'm going to kind of explain this with a more graphical interpretation. So for functions which are concave up, so functions which open up like this, any arbitrary function, it's concave upwards. So assume this is our x-axis. What we can say is that at this particular point, our slope, or our first derivative, is fairly negative. As we increase our x values, it becomes less negative, or less sloping, so even less negative, 0, positive, more positive, more positive, more positive. So as we increase x, so as x increases, we can come to the conclusion that our second derivative is increasing. It's positive because we're starting off negative and we're approaching positive. So it's like on the number line, going negative, getting bigger and bigger and bigger. So for concave upwards, our second derivative is increasing. Let's see what happens for concave down. So we're going to have our something like this, similarly like before. Start off any here. We see that our slope is fairly positive as it increases x, less positive, 0, negative, more negative, more negative. So as we increase x, our graph is going to become more and more negative. The slope is going to become more and more negative. So we see we're going from positive to, or going from fairly positive to fairly negative. So our second derivative is decreasing. That's how fast the slope is changing. So this is the slope. How fast is it changing? It's decreasing. So our second derivative, less than 0. Hopefully this is a better understanding for the second derivative. So